Okay, so next week we'll have a short quiz, like we have 15 minutes, and that will be the material that is for slow flows, up to slow flows. So whatever we did statics, we completed in the mid-sem. So this is from slow flows, all this thing related to the Moore-Coulomb theory and the critical state theory. And today I have put one, or I will put one homework assignment on Moodle, which will be due also next Thursday. So let me share my screen and let me review what we had done last time. So if you remember, we had started talking about rapid flows, but in the beginning of the lecture, we discussed one aspect related to bins and hoppers. That is, how can you calculate the mass flow rate coming out of a hopper? And what we saw is that, if the diameter of the exit orifice is larger than 2.5 times, if 2.5 times the orifice diameter is less than, or the height is larger than this, and the diameter of the hopper is larger than this, then the mass flow rate is found to be independent of these two quantities, and so it depends only on the orifice diameter. So if this is the case, then the only way we can define a velocity is using gravity and this one geometrical parameter which is important, which is d0. And the reason that is because the whole resistance to flow happens only at the exit. So when you assume this, that velocity is proportional to square root of g times d0, then it turns out then the mass flow rate should be proportional to rho b into v0 into the area. And if you simplify that, it comes out to be that the mass flow rate is proportional to v0, that is the orifice diameter raised to the power of 2.5 or 5 by 2. So Bevelou did a lot of experiments, and his experimental results he plotted as m raised to the power of 2 by 5 versus d0. Then according to this equation you get a straight line, and in fact he did get a straight line. But what he found is that the intercept is not 0 as it's over here, but it's at some positive value k times the diameter of the particles. And so if you fit a line to this, then the equation for the mass flow rate is given by this equation, which is the diameter of the orifice is slightly smaller than the actual diameter, and it's given by k times d0 minus k times dp raised to the power of 5 by 2. And it turns out k is about 1.5 for spherical particles, and this factor ranges between 0.5 to 0.65 for the different cases. So if we know this, then we can easily calculate what will be the mass flow rate. So it's a very useful correlation. Now, after that, what we looked at was rapid flow, and we saw that this is valid when the inertial number is larger than 0.1, and here the momentum transfer is by collisions and what is called streaming, that is the momentum being carried by the particles themselves as they move from one part to the other. And this is analogous to gases, so we can use kinetic theory approach. But there are of course differences. Particles are inelastic, there is friction, and there is a big difference in the size ratios. But we'll go ahead with that in any case. And we define two quantities: the mean velocity in any volume, which is just the number average, and the fluctuation velocity, which is the actual velocity minus the mean velocity. So this is the deviation from the mean. Now, by definition, the average of the fluctuation velocity is 0. But if you look at the root mean square velocity, that is always positive, and the temperature is then defined as just this root mean square velocity squared divided by 3. And it's a measure of the kinetic energy of the velocity fluctuations of the particles. Of course, if you remember kinetic theory, then you'll remember that in kinetic theory, the temperature is given by Kb, which is the Boltzmann constant times the temperature, is just mv squared by 3. So here we have dropped Kb and m. And we also said that in most of these cases, we can take the bulk density to be nearly constant because the spacing is small, but that doesn't mean that this, this is one parameter which is important, the spacing, and it will come in all our equations. And this is actually a measure of how close the particles are, and we'll see that a lot of the properties depend on S. So if we make these assumptions, then we get equations that look just like what we saw in fluid mechanics and heat transfer. The continuity equation is divergence of U is equal to 0. The momentum balance equation is given by this, which is exactly like what we get for fluid mechanics. And the energy balance equation is given by this, which is what we get in heat transfer. The only thing is that in heat transfer, you will get some over here, instead of 3 by 2, it is just, instead of this prefactor if you really look at all your heat transfer equations, you'll see that this is just rho times Cp. So, instead of the density into the specific heat per unit mass, we actually have just 3 by 2 into rho p. So that is a difference. That is one difference. And then the rest is the same, except we have one additional term, which is this, which is the loss due to inelastic collisions. So now we have a complete set of equations. At least these are the balance equations, and we need to find out now how to calculate pressure, stress, heat flux, and loss. So of course you'll remember that this term is the viscous dissipation, that is conversion of mean flow into the fluctuation energy, and conduction, which is the transport of fluctuation energy from one part to the other part of the system. Now, the theory also gives all these quantities that we wanted. So for example, we wanted P, that is given by this quantity, where alpha is just a dimensionless constant. And remember, I talked about S, this is the spacing. D is the particle diameter, T is the granular temperature. The stress is given just the same as a Newtonian fluid, 2 times viscosity into the rate of deformation tensor, where the rate of deformation tensor is given by this. And then the viscosity is a dimensionless constant eta 0 into rho b, diameter of particle squared, into square root of the temperature, this is the granular temperature, divided by the spacing S. And this is again, the heat flux is given by Q, that is the same as Fourier's law, minus thermal conductivity into the gradient of the temperature, where K is just given by K0, a dimensionless constant, rho b, particle diameter squared, root T by S. Just see, these two are almost identical. The only thing is eta 0 and K0 are different. And then there is loss due to inelastic collisions. In our notes, we are calling this as IE to make it different from the inertial number. So this is the loss due to inelastic collisions, and you can see that this is just given by this. Again, Here S is the spacing, epsilon here is the coefficient of restitution. So with this, all these equations, you can actually start trying to solve problems. And then today what I want to do is to look at a couple of examples where gravity is zero. So there's no gravity in the system. And the two examples we'll look at least we'll start looking at, are cooling of a granular gas. That is, you have a gas of particles in a box, and then they collide with each other, and because of inelastic collisions, the temperature comes down. So can we model that? And then supposing you have particles between parallel plates which are being moved at a constant velocity, so that there's a shear flow generated, and what will be the profile for that? So we'll try and look at these two things today.
Sir, Kunal here.
Yeah, go ahead, Kunal.
Sir, one thing to ask in the from the summary of the previous lecture. So while calculating the average velocity of the bulk of the molecules, so it would be vector average sort of thing, right?
It vector average.
Yeah,
But
yeah.
vector average is very easy. You know what that means is that you take the average of each component. That's all. And that is just like you. So you, if you have Vx, Vy, Vz, then just calculate Vx average, Vy average, Vz average. That will give you the vector. So this is just a short form way of writing it. The actual average is done by doing the average of each component and then using that as the final vector. Is that okay?
Yes, sir, got that. Thank you, sir.
Okay. So now let me just go to the other. Let me share my other screen with you. So this is what we had seen last time. All this we did last time. So it was, as we saw, it was lecture number 22. And now we will go on to lecture 23. So let's start with lecture 23. And does anyone know what the date is today? 23rd. Okay. Okay. So which is the first problem that we want to look at? How do we use these very complicated equations that we have put down? So the first example that we want to look at is cooling of a granular gas in zero gravity. Okay, so this is the problem. And what do we want to do? Let's say we have this box. And this has many particles. In this way, I've been able to fill it up with particles, and each of them will have some velocity. But there is no mean velocity. Okay. So what we want to say is particles are given random velocities at time t equal to 0, taking care that u is equal to 0. So the mean velocity is 0. So since this is a box, they can't go anywhere. So there's no mean velocity. But because they have some energy associated with these velocities, so even though the mean velocity is 0, the temperature is not 0. The granular temperature is some value T0. This is the initial temperature. There is one other parameter which is also important in this system, and that is spacing. So what we say is that the mean spacing is a constant. So actual spacing between any two particles is different, but if you calculate the average over all possible things, then the average value of S is just equal to S0, and that remains the same. And this becomes important because we've seen S appears in so many equations. So if S is changing, then we'll not be able to solve it. So here this is the assumption, and that makes sense because the average spacing, the particles will be all uniformly distributed. So if you take an average, then at any given time, this spacing will be the same, and it will not change with time. So these are the two things that we want to start with. So your mean velocity is 0. So now we can go back. This is a nice thing about all this online business, that I can just go back in my notes to remind you of what the equations are. So let's start with the continuity. So we'll start with the continuity equation. The continuity equation is divergence of u is equal to 0. Since u is equal to 0, so that means divergence of u is also 0. So we can write down over here that continuity equation is satisfied. So we don't have to worry about it. Since velocity is 0, so the first equation is already satisfied. Now let's go to the next equation, and that is
The momentum balance equation.
Yeah, this is the momentum balance equation. Here it is. Can you see this?
Yes, sir, it's visible.
Okay. So now we know that u is equal to 0, so the entire right hand side is 0. There is no gravity, so this term is 0. So we just have minus gradient of p plus divergence of tau is equal to 0. But now if you look at the definition of tau, you'll see from here that tau is equal to eta times d, and d is gradient of u. But since u is equal to 0, so then d is equal to 0, that means tau is equal to 0. So if you write down the momentum balance equation, then this is just rho bulk del u by del t plus u dot gradient of u is equal to minus gradient of p plus divergence of tau plus rho b into g. And then together with that, we have also as we have just seen, that tau is equal to 2 times eta d, and d is equal to gradient of u plus gradient of u transpose divided by 2. So we can clearly see that since u is 0, this term is 0, this term is 0. Since u is 0, so this is 0 and this is 0, so that means d is 0. That means tau is also equal to 0. So that means this is 0. And since it's 0 gravity, this is 0. So what this momentum balance equation essentially gives us is that gradient of P is equal to 0, or which means that P is just equal to 0. So the pressure is a constant that is, this is not independent of time. So maybe I should say this is P is equal to P of time only. So not, because gradient means, this is the derivative of pressure with respect to x, y, and z. So it doesn't vary with x, y, and z, but it can vary with time. So pressure at the most varies with time, and it's not dependent on x, y, and z. Okay, so this is what the momentum balance gives us. So really we are only left with one thing, and that is that energy balance equation. So again, I'll go back to remind you of the energy balance equation. And this is it. So over here, you can see clearly that if u is equal to 0, then this term will be 0, and this term will be 0. And then, of course, we have to see what is q. Q is conduction. Conduction depends on here it is. Conduction depends on T and S. But if we assume that everything, since pressure is uniform, so temperature also must be uniform. So if temperature is uniform, then the gradient of temperature will be 0. So then again it will give us that this conduction term is also 0. So now let's write down this whole thing, whatever I was saying. So we'll write the energy balance equation. And whatever I said, I'm going to redo. Correct. So this is all that you have. And what we saw is that maybe I should just write down one more thing here, which I mentioned, but I didn't write down. And the main thing is that if pressure is not dependent on, then this implies that temperature, and why do I say this? Okay.
Is also time dependent or something.
Temperature is time dependent. Of course, that's the main thing we want to find out. That we are doing cooling, that means temperature is changing with time. So let me write down the expression for P. You can see that it's just given by this. So that means P is just equal to alpha rho b dt by S0. So we can see that over here, since P is not dependent on X, Y, and Z, all the rest of the things are constants. So this implies that T is also not dependent on spatial coordinates. Okay, this is one of the things. This is the constitutive equation for the pressure or equation of state. So pressure is just proportional to the temperature. And if pressure is not dependent on spatial coordinates, then temperature also cannot be. So now we can go back to our energy equation and then start trying to simplify this. So straight off we get that since u is equal to 0, this term is 0. We have already seen u is 0, so this term is 0. Now we know that q is just equal to minus k gradient of t. But since t is not dependent on spatial coordinates, so that means gradient of t is 0, so this term is 0. So then this term is also equal to 0. So we are finally left with a very simple equation. And in fact, this is what determines the change in temperature with time. That is rho b into dt by dt is just equal to minus. So this is what in physical terms you can just say in very one line that the rate of change of temperature is simply because of the loss of energy due to inelastic collisions. Now what is IE given by? Well, if you look back in your notes, this IE has a simple formula. This is just equal to I0 into 1 minus the coefficient of restitution squared into rho b t raised to the power of 3 by 2 divided by S0. So this is a very easy equation for us to solve because you see that everything is a constant and the only thing that we have to worry about is, so we just get dt by dt is just equal to t raised to the power of 3 by 2 into everything else which is a constant. So what you will get is this is equal to 2 divided by 3. Rho b cancels out on both sides into I0 into 1 minus E squared divided by S0. Is that okay? Into t raised to the power of 3 by 2. So let's call this constant as just a for the time being. So now this can easily be integrated. If I bring t on this side and take that on the other side, so then what I will get is this is just equal to minus half so this is t raised to the power of minus 3 by 2 dt is equal to a times dt. So if we do the integral from 0 to t, so this goes from t0 to t. So if you integrate this, this will give you minus half t raised to the power of minus half integrated from t0 to t is equal to a times t. So this is just 1 by square root of t0 minus 1 by square root of t. So I've taken the minus sign into account so that I've put it as t0 minus t instead of t minus t0 is just equal to 2 times a into t. And so now if I want to sort of turn things around a bit, then what I'll get is...
Sir,
Yes,
sir,
have I
is
made
that
a...
80 by 2
Uh,
minus 2 t raised to minus 1 by 2?
minus 2, right? I put it as half. Right? Yeah, it has to be divided by, not multiplied.
Okay.
Because in my notes I have only put the final result down, so I was trying to do it here. Okay, so now if we want to get what is square root of t. So I'll take, this implies that 1 by square root of t is just equal to 1 by square root of t0 minus... Am I making some mistake somewhere?
Sir, I think it's okay.
So there was a negative term in IE. I think
There
you
should
missed
be
that.
minus. Yeah, that's it. That's what the mistake is. Correct. This should be minus over here. This is minus. So this is minus. Correct. So this is also minus. This makes sense. Okay. So this becomes plus a t by... So then, if I invert it, then I'll get square root of t is equal to 1 upon... I'll multiply... I just keep it like this just to make sure I don't make too many mistakes. And then what I'll do is I'll divide both sides by square root of... So what I'll do is multiply maybe top and bottom by square root of t0. So this is just square root of t0 divided by 1 plus a root t0 by 2 into t. And so, we can define a dimensionless time, tau, to be equal to a square root of t0 by 2 into t. Now this whole product has no units. If we bring back everything from what we had, what is a? So a is just 2 by 3 I0 1 minus e squared divided by S0, correct? So this is what is a, and then I have square root of t0 into T. And this whole thing is divided by 2. So tau is just equal to I0 1 minus so is this quantity dimensionless? So let's look at each term. I0 is a dimensionless constant. The coefficient of restitution is dimensionless. Temperature, what are the units of T0? They're the same as velocity squared. So this square root of T0 has units of velocity, that is distance by time. Multiply that by time, so this has units of distance, and S0 has units of distance. So you can see this whole quantity is dimensionless. So this is a dimensionless time. Okay. So now if we look at this, we'll see that if we define T bar to be equal to T divided by T0, so then this gives us that square root of T bar, that is the dimensionless temperature, is just equal to 1 upon 1 plus tau, or 1 by square root of T bar is just equal to 1 plus tau. So this is quite a famous result, and it is called the half law. He was the first one to show this. And what it says is that if we plot 1 by the kinetic energy of particles versus time, then you will get a straight line. Okay. This is something that we have seen from all our simulations. But this doesn't work and for all times. And what actually happens is that as long as the particles are homogeneous, as long as this condition that the mean spacing is uniform everywhere, as long as that condition holds, then the half law is okay. But there is actually an instability in this system which leads to clustering. So the S becomes spatially dependent, and then the theory no longer works. Okay, and I can show you one image of that. And this is I'll put the reference down for this. Oops, so this is not what I wanted. And let's see if it works. I'll try and just paste it into whatever I'm showing you. Here. I don't know if it'll work or not. Anyway, What I'll do is I'll show you in a okay, it's come now. So this is what happens. So you start with a large number of particles, and then, you know, because of this instability, this spacing is no longer uniform. So, you know, you can clearly see that some particles are clustered together, and then the half law breaks down. Okay, and I'll put up the research paper in which they have shown this. Why does this instability occur? Well, if you just imagine that there is some region, because of some fluctuation, there is a slightly higher density and or a lower spacing in that region. So wherever there is a lower spacing, so if S0 is smaller, then if we go back to this equation, wherever S0 is smaller, this dissipation will be higher, and so the rate of cooling will become more, and so the dissipation will become even higher, and as a result, you know, the spacing will go on reducing, and the particles will cluster like this. And so as more and more particles join the cluster, you get these kinds of structures forming. Okay, so this is the first example I wanted to show you. Let me show one more example problem. And that is the second example I want to look at is steady shear flow under zero gravity. Why are we always using zero gravity? Well, when we do some problems which include gravity, you'll see that gravity creates its own complications. So when you have zero gravity, then the theory is a lot simpler. So let's say we have parallel plates. Which are separated by some distance h. And let's suppose we have a coordinate system in which this distance is called y and this distance is x. And let's suppose the bottom plate is stationary and the top plate is moving with a velocity capital U. And we'll also assume that the temperature or the fluctuation velocity is zero on both walls. And so what we are expecting is that there will be some sort of velocity profile that looks like this. There's zero velocity here, mean velocity. So, you know, you'll get some sort of velocity profile like this. And so we want to find out what is this velocity profile. So if we write down, we can start with writing down the boundary conditions first. And for this, we can imagine that ux is equal to 0 and v is equal to 0 at y equal to 0, and then ux is equal to capital U and v is equal to 0 at y equal to h. So these are the simple boundary conditions that we have. And now let's write down all the governing equations. And the first one we'll always write is the continuity equation. And this gives us if we write down the continuity equation for this case, we are assuming that only ux is the non-zero component. And so this tells us that dux by dyx is equal to 0. And so that tells us that ux is only a function of y. Then if we write down what is the x momentum balance equation. Now here I'm going to just leave out a lot of the terms because it's a steady flow. So if we go backwards in time and look at all of these things, momentum balance equation, where is it? Here is the momentum balance equation. So you can see that since it's a steady flow, so this term will be 0. Since a unidirectional flow, so then u dot gradient of u is 0 because the velocity, the gradient of the velocity is orthogonal to the direction of the velocity. So this term is 0. So the whole left hand side is 0. You'll have some, you'll find we can show that gradient of p will also be 0 because there's no dependence on x. So in the x momentum balance, you'll see that this is 0, and in the y momentum balance also we'll see 0. And then we have this term as non-zero, but there's no gravity, so this is 0. So, in here, we'll finally just get the left-hand side is 0. This, I'm just going to write down this. In the x momentum balance, you'll have del p by del x plus del tau xy by del y. Now, this is the only non-zero term because you only have one component of the stress which is 0. All the other stresses are, so tau xx, tau xz, everything else is 0. So this is what you get. And since we don't have any dependence of anything on x, so this term will also be 0. So basically you get that the shear stress is a constant. So this is a constant. So it doesn't vary with time or space. So far this is what you would get for any. This. And the reason I'm going fast is because if you did this problem even for a Newtonian fluid, you'll get exactly the same answer. And if you write down the y momentum balance equation, then again left hand side is 0, and then you'll get minus del p by del y, and then you'll see all the terms are 0. All the other terms are 0. And so this also tells us that p is a constant and equal to p0. So you will get this. This is nothing to do with granular materials and rapid flows or anything. If you take any fluid between parallel plates and you assume these things, then you will always get this. So this is going to give, you're always going to get this. So that in a shear flow, which is unidirectional, you always have ux dependent only on y, and the shear stress and pressure are constants. So that is a standard thing. So this is nothing to do with granular material so far. And then you'd also have the energy balance equation. Again, here also this is same. On the left hand side, everything is 0. And you'll have the viscous dissipation is non-zero. This will give us tau 0 into dux by dy. And then you have a conduction term. which is d by dy of k into dt by dy, and then you have, of course, the loss due to inelastic collision. So these are the equations. So this is what you have. So the first three equations don't give us anything much beyond saying that u depends only on y, tau 0 and p 0 are, I mean tau xy and p are constants and equal to okay. So now let's look at what happens for granular systems, and for that we have the constitutive equations. And I'll just write these and then stop. So you can see that first equation is for pressure, which is just alpha rho b into d times T by S. Now S will also vary, T is also varying, but this product of everything is just P0, which is a constant. So this is one equation. Then you'll have tau xy, tau xy is just equal to eta 0 rho b d squared square root of T divided by S into d ux by dy. And since tau xy is equal to tau 0, we can turn this around, and this gives us that the velocity gradient dux by dy is just equal to tau 0 into s divided by all this other stuff, which is equal to eta 0 rho b d squared into square root of t. So here you have an expression for and in fact for this one you see that there is a relationship between S and the temperature. So if you want to write down, you can say that S is just equal to alpha rho b d p divided by the pressure, and that pressure is just a constant, which is so from the two constitutive relations we have got one expression for S, one expression for dux by dy, so we can just substitute for one inside the other and get rid of it. And then we have the constitutive equation for K, which is important in the energy balance equation. This is just K0 rho b into d squared square root of T divided by S. Okay, and then you have I for inelastic collision, that is just I0 into 1 minus E squared rho b T raised to the power of 3 by 2 by S. So if we look at all these equations, so we can see that the unknowns are ux, t, and s. So these are the three unknown quantities, and then we essentially have the three. We have essentially the three equations, which are this is one equation, the energy balance equation, and then we have two more equations which come from the constitutive relations. So you can substitute for S and dux by dy in this using this. So we will use this to essentially solve in the next class. And what I'll show is that if I substitute for everything into the energy balance equation, that is substitute for dux by dy in the energy balance equation and then simplify it out, then what I will get, I'm going to do this again next time, so just to write down the final result, I'll just get tau 0 squared by S this is just substituting for dux by dy, so that is the first substitution. Substituting for k, okay, and then of course I0 as it is, IE is just as it is. So now you have one equation. So what I did was, all I've done is in this equation, I substituted for dux by dy using this and k using this. And so now I've got an equation, and now there are only two variables. Now I have two equations and two unknowns. And so in the next step, what I'll do is I'll substitute for S in this equation. And then I'll have an equation only in terms of the temperature. And when I do that, then I have a differential equation for the temperature, which I can solve. Okay. So with that, I will stop. And please have a look at the Moodle site. Homework assignment 2 will be up very soon.